So, good morning to all of you. Today, we'd like to concentrate on two things here. Number one, yesterday we have seen something about this particular algorithm, MaxMin algorithm. So already we have seen this particular algorithm and how the things are being happening. What are the primitives which we have to consider for the MaxMin algorithm? We have seen everything. Okay, we have seen everything here. So it is basically comparison operations are binary operations, so that we require two different elements to be checked for comparison. So that is why first condition will be there with you. Then time complexity, number of comparisons for first condition is 0. Second condition is I equal to j minus 1. That one comparison will be gets happened here. Therefore, you could get a minimum and a maximum if two elements are there. Then followed by more than so two elements will be there with you in our list. Then you have to identify or you have to follow the general primitive of what is the divide and conquer algorithm. We need to identify the mid element here. Yes, mid element is being identified and call so. And then we have to follow this particular condition while it is being combining. This operation will be done while it is being combining. Okay, already we have seen the example also in the previous lecture. Okay, this is the previous lecture which has been recalled. Now, let us consider today's lecture. So, algorithm is gets over and the example also gets over and the primitive basic information also gets over for minimum and maximum problem. Now analysis. You please remember, so t of 1 will be equal to 0 if n equal to 1, and if n equal to 2, t of 2 equal to 2. Whereas if n is greater than 2, then you have to identify the mid element and you can perform. Please keep all this in your mind. Then we'll move to next analysis part. And if analysis part is completed very quickly, then we'll move to quicksort also today. So look at this. We are trying to explain something about this complexity or analysis part of MaxMin or MaxMin algorithm here. Look at this time complexity. So in this analysis of this particular time complexity, we must be always concentrate on number of comparisons rather number of other operations. Number of comparisons will be very important because we are trying to specify maximum and minimum. So if you want to specify maximum, so maximum is always trying to take some greater than or less than operator. Minimum also same. Minimum also same. Based on the user's perception, so you may be operate either it is greater than or less than any one of these operators. So comparisons are very important while calculating MaxMin algorithm using divide and conquer. So that's a very important point we need to keep in our mind while we have to evaluate the complexity of MaxMin. Then. So only one element. Already I have given this information. Even then, for analysis part, I'd like to take it into consideration. So only one element is there with you. If single element could be there with you, then what you are supposed to do? So no comparisons are required. Comparisons are not much. No comparison will be required. So therefore, t of 1 will be equal to. So t of n will be equal. T of 1 will be equal to. So 1, let us consider this is equation number 1. Okay, that is the equation number 1 here. Then followed by if number of elements will be 2, then what exactly we are supposed to do here? So if number of elements will be 2, so one comparison will be required. So single comparison will be required. So therefore, based on single comparison, yes, we have to identify. So then T of 2 will be equal to 1. So one single element, no comparisons are required. So complexity will be 0. If two elements will be there, one comparison is required. One if condition is required. So T of 2 will be equal to 1. So therefore, it could be considered as second equation. Okay. Then go ahead with if more than two elements will be there in our elements, in our list of elements, then we have to take the algorithm. We have to take the algorithm, divide and conquer algorithm, what we have defined just before, and we have to done it. Okay, how this could be done? So look at this. P of n will be equal to, so for finding minimum or maximum, whatever it may be, for minimum, let us consider this is for maximum, this is for maximum, and this is for minimum, this is for minimum. For example, so these things will be gets happened here. These things will be gets happened here. Then plus 2. It could be so plus 2. If n is greater than 2, obviously 2 comparisons will be gets happen. And for recursive calls, so this could be for minimum and this could be for. In this way, we would like to consider that. The problem can be solved by using substitution method. The equation will be done in identify the next value for t of n by 4 and identify for t of n by 8 and so on and so forth. Then you could get some other equations based on those equations using substitution methods. You can perform the operation. Let us so here. If you solve this particular equation, you could get T of n equal to 2 into T of n by 2 plus. Okay. So let us consider this is equation number 3. Then go ahead and solve these equations. So identify the values of T of n by 2 and T of n by 4 and T of n by 8 and so on. Let us consider. So T of n by 2 value will be equal to, so look at this, 2 into T of n by 4 plus 2. Because n by 2 into half. N by 2 into half will be equal to n by 4. 2 into T of n by 4. So total list, given list of elements will be divided into 4 halves. That is the meaning of this one. That is, this is equation number 4. And identify the value of T of n by 4 here. T of n by 4 will be equal to, so 2 into T of n by 8. Because in the next recursive call, total list of elements will be divided into 8 halves. 8 sublists. Let us consider this is equation number 5. What we are trying to do here, already we told you that it could be done by substitution method. So these two equations will be substituted in this particular equation. We could get some value. Let us consider here. Look at this. Substitute equation number 4 and 5 in equation number 3, then you could get this one. This is our actual equation number 3. Then 2 into substitute the value of so T of n by, so this is T of n by 2. If you substitute this particular value, 2 into so 2T n by 4 plus 2 plus 2. This 2 will be as it is. You can take into consideration as. Then if you evaluate this one, 2 into 2 square of T of n by 4. So 2 into again 2 2s are 4 plus 2. Okay. Then substitute the value. So this particular thing will be taken from so equation number. So let us consider it is from 4. And here T of n by 4 value could be substituted. So this could be taken from equation number 5. This is equation number 5. This whole equation is from 5 and this whole equation is from 4. So however, so 2 square into 2t n by 8 plus 2 plus 4 plus these values. I don't want to add these values. These values will be as it is. I'd like to place as it is here. Now evaluate this one. So 2 square into 2 will be equal to 2q plus t of n by 8. So 2 square. So 4 into 4 to 8. And this will be taken as it is here. Okay. Now, so let us consider this particular equation will be. Consider these values will be So form with respect to 2 powers, 2 cube, 2 square, and 2 power 1. Then evaluate this one. Let us consider this is equation number 6. So here, what is the minimum? What is the value for the small of p? Small of p value equal to 2 here. As and when small of p will be taken, this problem can be taken with the 2 sublists, then small of p will be returns true. Until unless it could not be returns true. If any sublist does have, for example, if any in our example we have seen at 3, so we have 25 and it is only one element which is available with us. That to satisfy the small of p value, so we have to duplicate it with the same. So with the same index value and with the particular value. So like this we have to duplicate it, then we could identify the minimum and maximum from this one. So however, small of p will be taken 2 elements in the sublist. So therefore, as and when you have 2 sublists with you, then the problem will be, so the small of p will be returns true. So keep this one in our mind. So let us consider, so that is what I have given the same explanation to you here. So small of p will be satisfied when your sublist might be having exactly 2 elements. That is the explanation I have given in terms of so this one here. So if you consider this one, then what we are supposed to do? So n elements will be, we have n elements and you are supposed to do 2 of k minus 1. K minus 1 recursive calls. K minus 1 recursive calls will be done here. Okay. If you do k recursive calls, obviously small of p will be taken singularly. Please try to understand. Each sublist must be having 2 elements. Each sublist must be having 2 elements here. So because of this particular reason, k minus 1 recursive calls will be done here. K minus 1 recursive calls will be done here. So it must be there in our mind. Keep this particular point in your mind. This is very, very important point you have to remember while doing some kind of exercise with the max and min problem. But actually, as far as our divide and conquer operation, so what is the primitive, basic primitive? N equal to 2 power k. So you don't change this particular basic primitive for any problem. Considerations must be taken. That's all. You have to take considerations. Now, so you have to take this particular equation and substitute this equation in equation 6. Before going to substitute this particular equation, so here it is 2 power 3, and here also 2 power 3, and of course you have to take this particular point or this particular expression aside. And if you consider these two, it is 2 power 3 and it is 2 power 3 and n. What is the value of n here? 2 power k. Okay, so here I'd like to consider, for example, k will be equal to, because already, so in 2 powers already I have 3, so that k will be equal to 4, for example. Totally 16 elements are there. For example, if k will be equal to 4, what does it mean? So n will be equal to 16, for example. N will be equal to 16. So therefore, so 16 divided by 2 power k, that is 2 power 4 will be equal to 1 actually. So how many number of recursive calls will be done? If you do, so 4 recursive calls, obviously your sublist elements will be single, only 1, 1, 1, 1. So therefore, instead of doing this particular job, what we are trying to do? So 16 divided by, so 2 power 3, that is k minus 1 will be leads to you 2. 16 by 8, that equal to 2. So each sublist might be having 2 number of elements. Each sublist might be having 2 number of elements. So therefore, if you consider k will be equal to 1, then this equality will be get satisfied. This equality will be satisfied for this equation. I'm talking about this with respect to this particular equation only. Okay, 2 cube, n by 8 in the sense 8 will be also written in 2 cube. So what does it mean? N must be equal to 2 power k. N must be equal to 2 power k. And how many number of recursive calls will be gets happen in MaxMin? K minus 1. So therefore, I'd like to consider I'd like to consider, so k will be equal to 4. Therefore, where exactly n that could be operated 2 power k, where exactly 2 power some value k 2 power 3, thereby you have to operate 2 power k minus 1. Okay. So next one is that operation only you can see here. If k will be equal to 4, then what exactly it could be? So you please remember here that operation will be takes place something like this. So T of n will be equal to 2 cube into T of n by 8 plus 2 cube plus 2 square plus 2 power 1. This is the actual equation just before equation. So substitute k equal to 4, where exactly? If k equal to 4 in the sense, number of recursive calls will be k minus 1. That is 2 power k minus 1, n equal to 2 power k, and 8 in the sense 2 power 3, that is 2 power k minus 1 also here. This is constant expression. Don't worry about this expression. Now look at this. 2 power k, 2 power 4 minus 1 into 2 power 4 by 2 power 3. So that is 2 power 4 in the sum 16 divided by 8 will be equal to 2 t power 2, t of 2, and this expression will be as it is. Hope that you do understand what I'm speaking here, what I'm delivering the lecture to you. Then, so if this continue this particular process for k recursive calls, it could be done like this. 2 power k minus 1 into t of 2 plus. So this expression will be continued for k times here. 2 power k minus 1. So here, if k will be equal to 4, if k will be equal to 4, here it is the value which is pertaining here will be k minus 1. So therefore, number of values here will be equal to 2 power k minus 1 plus and so on plus 2 cube plus 2 power 2 square plus 2 power 1. Okay. Now you can see this one. So 2 power k minus 1 into 2 t of 2 plus, if you make them into one sigma expression something like this, I 1 is less than or equal to I is less than or equal to k minus 1, which is 2 power I. Okay. Now you can see this one. 2 power k minus 1 into 2 t of 2 plus, if you solve this particular expression, so 2 power k minus 2. This is 2 power k minus 2. Okay. Then, so t of 2 will be equal to, from equation number 2, I hope that I have written, no, I did not written here. So instead of equation 2, t of 2, sorry, this is not t of n actually, this is t of 2 actually, sorry. This is t of 2 actually, this is t of 2 will be equal to 1. Since it is 1, it is 2 power k minus 1 plus 2 power k minus 2. And let me write 2 power k minus 1 like this. 2 power k, so divided by, so 2. Will it be okay? Yes, it could be okay. Okay, 2 power k divided by 2. If you bring this particular 2 to the power, something like this, Vishnu. So same problem. Yesterday also we faced the same problem. The problem is power cuts. Yes, today also power cuts are there. I'm sorry for this. Okay. So it could be written something like 2 power k divided by 2. So therefore it could be also, if you bring this one here, so this equation could be seen. So 2 power k, so into, so 2 power minus 1 will be leads you 2 power k minus 1. Okay. So therefore, I'd like to write 2 power k minus 1 into 2 power k divided by 2. and solve this particular equation. So it could be seems like this. Solve this particular equation in the sense. So you could consider 2 power k divided by 2. So plus n. 2 power k in the sense n from equation small 1. So plus n minus 2. If you solve this particular thing, LCM will be equal to 2. That is 2 power k. Okay, here also 2 power k instead of 2 power k, I'd like to write it as n here. So this is n plus 2n, so minus 2 2s are 4. Okay, it will be leads you. So 3n minus 4 divided by 2. So this is not a pure mathematics. So that I'd like to separate these two terms. That is 3n, so divided by 2 minus 4 divided by 2. That will be leads you 3n divided by 2, so minus 2. Look at this. Okay, in this way you can find the complexity. So previously we have seen one example, that is 9 elements are there with us. 9 elements are there with us. So n will be equal to 9. So Navy approach, general approach, if you consider the general approach, so 2 into n minus 1, that is the actual operation we got. So that equal to 2 into, so sorry, it is 10, I think. Sorry, it is 10. It is 10. Previously we have taken 10. So 2 into 9, that is 18 comparisons will be required in Navy approach. Whereas within this particular thing, by using this particular equation, so 3 into 9, 27 divided by 2, so minus 2. 27 divided by 2, 26 in the sense 13.5, okay, 0.5 will be eliminated, 13 minus 2, that is 11 operations will be, 11 comparisons will be required to find minimum maximum when compared to Navy approach. So here it is 18, here it is only 11 for 10 elements, so which is very, very, very better performance when compared to the Navy approach. Okay, so this is what about the complete complexity analysis in terms of MaxMin problem. And I'm expecting some kind of questions from you people, but you are not giving any questions, or you are not posting any questions on the lecture through Google Classroom. I don't know what was happened. Okay, so somehow this is complete information regarding to MaxMin, so complexity. So I'd like to prepare one particular program by using divide and conquer method, and I'll forward the same problem to you through Google Classroom probably by today in the evening. Okay. Now it's time to define something about very important sorting algorithm in the world. Very, very, very important sorting algorithm in the world, that is quicksort. Okay, actually MedSort is the first sorting algorithm whichever introduced to the world by one very, very pioneer of computer science. Just wait for a while. So one pioneer is there. He is Sir John von Neumann. He is the person who introduced the first sorting algorithm on divide and conquer technique. Actually, divide and conquer technique are also devised or also found by Sir John von Neumann, who is father of modern computers or electronic computers. He is the person who was identified the sorting algorithm. That sorting algorithm is merge sort. Even then, I'd like to. I'm interested to specify only quick sort in the beginning. Then we'll go for merge sort. Okay. Let us take quick sort here. So 50% of quick sort will be taken today, and remaining 50% will be taken by tomorrow, because already 28 minutes have completed out of 40. So let us take this one. Okay. Of course, this will be. Yeah, quick sort. What is the quick sort problem? And it is also very, very important to recall or remind the people whomever introduced this particular algorithm. Let us take some remarks. So remarks in the sense, what is the actual points which we have to take into consideration while Quicksort is being operated on the given list of elements. Okay, look at this. It was actually introduced by Tony Hoare in 1962. MedSort was introduced in 1942 itself. After 20 years of MedSort, it was introduced. Okay, and it is strictly applied this divide and conquer algorithm. The technique is going to be took place. Then it's very important to remember this algorithm is in place algorithm. This algorithm is applied in place algorithm. In place in the sense, without using extra space. It is not supposed to use any extra space for doing some kind of operations. I mean, for doing some kind of, for storing some kind of sublist. Okay, it is not supposed to do like that. So what is meaning here in the sense? So rearranging the elements where they are. For example, so some list of elements are there with you. So some list of elements are there with you. So always sorting also involves some kind of comparisons only. So here this element is greater than this particular element, then these two will be swapped. So here itself swapping gets operated. So that's all. That's all. It should not be take another list of elements and they have to perform swap here. Something is not supposed to be done. Something is not supposed to be done here. Okay, that's what you need to keep in our mind. So that is why it is called as rearranging the elements where they are, where exactly they are. That could be operated rearranging. So therefore, no extra space is required. So for example, if you are trying to so otherwise 10 power, for example, 10 power, some 20 number of records of a file is being so sorting. So each record size will be, for example, 1 kilobyte, otherwise 1 megabyte if you want to perform. So if you want to do the same kind of operation by using merge sort, it must be required 1 terabytes of space. 1 terabytes of other space is required. So that is the problem with merge sort. However, so this is the no extra space is required, where exactly the data will be, thereby, so the data will be operated. Then it is very much efficient because no extra space is required, so that it is very much efficient in terms of storage. Extra space is not required. Extra space is not required. Then it is very practical and tuning in terms of sorting. Tuning in the sense, so very fast algorithm provided. Tuning in terms of sorting is, I'm not supposed to agree this particular point, but it must be written because if data will be at random, data will be at random, or data will be at random, the performance will be big O of n log n, n log n. So if data will be either it is in descending order or it is ascending order, for example, ascending order. If these two will be, I mean 1, 2, 3, 4, this is ascending order. So 4, 3, 2, 1, this is descending order. Okay, descending order. If data will be there like this, then it is a big O of n square. It could be gets operated big O of n square. Remember this, it could be operated big O of n square. Okay. So that is why in terms of sorting, so in terms of sorting, it is a perfect tuning in the sense, if your data will be available in such a way, it is very, very worst. But if data will be at random order in the sense of 3, 2, 4, 7, 8, something like that, random order, it's okay. It's very, very, very efficient to be done. Okay. Then, what is the actual problem to be done here? The problem is, as usual, it is a divide and conquer technique kind of a problem. Already we have given this particular statement here in the remarks. So it could be always operate, so divide operation. So how you could perform this particular divide operation here in the sense, total number of elements will be divided into two sublists by taking one specific element. That element is called as a pivot. That element is called as pivot. So look at this. What is that particular element here? That is a pivot. So in our problem, the pivot will be considered as x. Okay, that is called as a pivot. And after performing the whole operation, so for one recursive call operation, then array will be divided into, so lower sublist elements is less than x and the higher sublist elements will be greater than that particular x. So what does it mean? It could be seen in a way. So x place will be here, then whatever the elements which will be available from here to here will be lesser values of x, and whatever the elements you have to identify here will be greater values of that particular x. So this is the first operation. Then second operation will be you have to conquer, that is recursively you have to operate, or you have to sort the two sublist arrays. Combine. So while operating this conquer operation, obviously implicitly this combine also be done. Okay, because already we have given it can be sorts in place sorting algorithm. Okay, it is in place sorting algorithm. So therefore, combine and conquer both will be actual process, and combine will be implicitly single operation. Okay, so therefore, here while writing this fixed sorting algorithm, partition algorithm, this partition algorithm is partition function is very important. If you learn this partition step in a proper way, yes, it's very easy to understand. Okay, I hope that many of you have submitted the quicksort algorithm to me, and let me explain that particular quicksort algorithm also by tomorrow. And is that a quicksort algorithm what you have suggested or what you have submitted is feasible or not? Let us explain by tomorrow. Then how quicksort will be developed by using big O of n log n. How this could be developed by using big O of n log n. You must remember here big O of n log n, n base to log n is a lesser value. So n log base to n value is a lesser value when compared to n square. When compared to n square, so it is very much less value. Since it is very much less value, so your algorithm, whatever the problem you have submitted to me, all those problems will be gives this kind of complexity. What I am going to explain you, so that is going to give you n log n. So let me explain by tomorrow because the time is running out. So tomorrow I shall explain the complete information. Okay. Now let me close this particular point. Don't go away. By tomorrow, so we'll go ahead and don't go away. I'd like to take some attendance of you. Please wait one moment. If you left out here, then you could not get any attendance.